Hello guys, in today's lesson we're going to talk about the chemical kinetics, and at the beginning of the video I'm going to talk about the introduction of it, the reaction rates, and the dependence of rate on the concentration. So let's start by chemical kinetics. So what is so an important statement that we should know is thermodynamics. So what is thermodynamics? Thermodynamics is a reaction energy and stability of product is described by thermodynamics. So in thermodynamics, what thermodynamics describe is a reaction energy and stability of the product. So thermodynamics describes reaction energy and stability of products. And now we're going for what chemical kinetics means. So chemical kinetics is the study kinetics is the study of speed of chemical reaction, and rate, in which reactants are converted into product. So converted is also another keyword, and the study of the speed of a chemical reaction and rate in which that the reactants are converted into products is known as chemical kinetics. So now let's talk about that's what chemical kinetics means. So let's talk about the average rate of reaction. So what is it? The average rate is defined as the change of in concentration of whether reactants or products over the time. And so to give you a bit of visualization for it, let us consider the hypothetical reaction A to B. And the data for example, we have time here, we have A concentration, and we have B concentration. So the time that it takes, like for example, it's in minutes. So at time 0, the A concentration is 1 molar, the B is 0. So there's 0 molar of like B present in the reaction at the beginning of the reaction. And after 20 minutes, the amount of A present would be like, for example, 0.54 molar. And after 40, it would be, for example, 0.3 molar and 13. So this one, the number should add up, 0.46 molar and 0.7 molar. And how are we supposed to calculate the average rate formation of B? The average rate is changing delta concentration. The change in concentration of C, I'm showing C as a concentration of B over delta T. So the overall formula, it's just like that, delta concentration of B over delta T. So for example, in this case, for the first 10 minutes, first 10 minutes, it would be, we just divide that by 2. Okay, let me just draw it like this. The average rate (0.26 molar minus 0, because we have 0 here, 0, and we just have to like divide the initial minus this one to get like the change of it. And so the change after 20 minutes is 0.54. However, since we want it at 10 minutes, so we just have to divide that 0.54 by 2, and it's in 20 minutes. So in 10 minutes, it should have been like 26. And so minus 0 molar over 10 minutes. It would be 0.026 molar over min. So if we were like to perform the actual experiment, we could calculate the average rate of formation during each like 10 minutes. So what is the rate of formation versus rate of disappearance? So in this example, we calculated the rate of formation, and we also can like calculate the rate of disappearance. So now we need to calculate the rate of disappearance for A, because A is what we are consumes here. And for the rate of disappearance, since for example, because this here now it's like half of it would be 46, half of 46 is 23, so it would be 0.23 minus 1, right? Since we don't want a negative answer, the rate of disappearance is negative delta A. We put a negative sign over delta T. So now, what is the relation between the rate and stoichiometry? So, for example, consider this reaction. This is an important one because we're going to work with it a lot. 2NO plus O2. All of them are in gas states, and so there should be some questions. So how do we calculate the instantaneous rate? And how does the rate of formation of NO compare to the rate of disappearance of NO2? And how does the rate of formation of NO compare to the rate of formation of O2? So in general, for the reaction, if you have a reaction like this is the coefficient of A plus B is the coefficient of B plus C plus D. The general rate would be, let me move it here. The general rate for this one would be negative, because these are the disappearance ones, so we should put negative for them. Negative 1 over the coefficient over delta T delta A is equal to negative 1 over B times delta T. I should put the delta, I'm sorry, delta out of bracket, delta B equals to the 1 over 3 C. There's no equal here. Delta T, delta C concentration equals to the 1 over D, delta T, delta, D. And that's how we calculate the rate, because these are the disappearance one and these are the formation ones. These two. These are the formation and disappearance. So as we said here, we put negative here. So using the formula that we have, like the equation that we have, it was 2NO2 produces 2NO plus O2. So the rate would be negative 1 over 2 times delta T delta NO2. delta NO2 concentration equals to the half delta T delta NO equals to the delta T delta concentration of O2. And if I want to give you another example to calculate it, so the composition of N2O5 proceed according to the equation of 2N2O5 produces NO2 plus O2 and 4, so the coefficient of NO2 is 4. And if the question asks for, the question says, if the rate of decomposition of the N2O5 is 4.2 times to the 10 with the power of -7, what is the rate of appearance of NO2? So NO2. So how do we calculate it? We say, as we said, the rate of them are same. So -1/2 of, for example, rate, because that is our rate, right? This is our rate. This is our coefficient. So rate of N2O5, 2O5, which is delta N2O5 over delta T equals to the 1/4, because our coefficient is 4, rate of NO2. So how do we calculate it? We say, if we multiply it by 4 to say, okay, so we want to calculate the rate of NO2, and to simplify it, we just multiply it by 4 to get rid of this coefficient, and multiply it by 4 would be -2 rate of NO2 into N2O5, and the rate of N2O5 was okay. So, and since this is the rate of decomposition, and so we just have to put the negative sign here, and so the final answer would be -2 times -4.2 with the power of 10 with the power of -7. So the final answer will be 8.4 times to the 10 with the power of -7 molar. That's the rate for NO2, I'm sorry. For the O2, again, we say that -1/2 rate N2O5 equals to the rate of O2. And now, so rate of O2 oxygen equals to the -1/2 times to -4.2 with the power of 10 with the power of -7. So the final answer would be 2.1 times with the power of -7 molar. That's the rate for O2, and that's for NO2. And that's how we calculate it. For the dependence of rate on concentration, so let's consider this equation here. NH4 plus NO2 negative gives N2 plus H2O, and since we have 2 H2O, and so there is a series of experiments were performed, and I have the numbers of it here. Okay, so that's our, I would write it as XP experiment. Initial, I would put I as an initial of NH4 concentration. I would put I as initial of NO2 concentration, and I would put rate here. For the experiment, how many experiments did it? Okay, 8. 1, 2, 3, 4, 5, 6, 7, 8. The initial of concentration of NH4 was 0.0.1. Okay, for for the first 4 experiments, they put the initial volume of NO2 as a constant, and for the in the second phase, the initial concentration of NH4 was constant. So for the first 4, 0.2 was a concentration, 0.2, 0.2, and 0.2. And for the after fifth experiment, they put NH4 concentration constant, 0.2, 0.2, and 0.2. They initially changed and increased it like each time the concentration of NH4, and by like it's twice here, it's twice now, and I'm sorry, twice, again twice, but like 1.5, 0.06, and again for here it's twice, 1.5, 1.5. And as you guys can see, the rate, for example, for this one is 5.4 times to the -7. For this one will be 10.8 to the power of -7, because it's twice as that. And if you can guess it, for this one was 21.5 to the 10 to the power of -7, and this one is 1.5, so this one will be 32.3 times to the power of -7. And again for this one, in the second phase, it's almost similar to this. So same number were found, 10.8 to the 10 to the power of -7, 21.6 to the power of -7, because they're also similar, as you can see, and 32.4 to the power of -7 were found, similar to this. And here we get a number 43.4 to the 10 to the power of -7. So as you can see, there is a linear relationship between them. And now we're going to talk about the rate law and the reaction orders. So as we increased it, as we increased the concentration, like the same amount was like the same relationship, like this is twice, and this is twice, this is twice, this is twice. This is 1.5, and this is also 1.5. There's like a twice the concentration over here, and there's like a twice concentration rate over here. So we can conclude that the rate of reaction depends on the concentration, and this formation can be expressed in form of the rate law. And rate law is an expression that shows how rate depends on the concentration of a reaction. And how do we show it? It's like this. Rate is equal to K. K is a rate constant. NO2 negative times NH4 positive here. And if we know the rate law and the reaction, the rate of set for a set of reactant concentration, it allows us to like calculate the value of K. And don't worry, they will give you the rates on the exam if you have. I mean, when I was studying my course, like the second general chemistry, when we learn about this, we had like the rate, the set of data that we need for the concentration of the reactants or like productions and everything. So you just need to calculate the rate of rate constant, and then so on in the question. And if I want to give you an example on how to do it, for example, in the experiment A, the rate is 43.4 times to the power of -7. So rate is 43.3 times to the 10 to the power of -7 equals to K times what was the concentration of NO2 here? 0.2 times 0.0808. So the K here, how do we calculate it? we just say K equals to the 43.3 times to the power of negative 7 equals to the 0.2, what? Times to 0.088. Sorry guys, it's just, so the answer would be the answer is 2.68 times to the 10 to the power of negative 4 molar per second. No, I'm sorry. It's not the right unit for it. We show it as, because the moles goes down, okay, it goes up. Liters times mole per negative times seconds in negative. And once we know the rate law and the rate constant, it is possible to calculate the rate for any set of concentrations. So now we have the rate constant here. We can just calculate everything now here using the rate constant that we have, and that's it. And now we can go for the reaction order. The rate laws for most reactions will have the general form of rate is equal to the K reactant 1 to the power of M. It's the coefficient of it. Reactant 2n. The exponent m and n are called reaction order, and the sum of the exponents m plus n is the overall reaction order. So m and n are what? The reaction orders. And m plus n is the overall reaction order. If we want to consider the rate that we for the last experiment, rate is equal to the K NO2 NH4. So the M here is 1 and the N here is 1, 2. So so what we can say about this equation is that the reaction is first order in NO2. NO2 is first order because its M is 1. And H4 is also first order. But what is the overall order of the reaction? It's the total of M plus N. So 1 plus 1 is equal to 2. It's the overall order. So the order is a second order. Overall order. And the reaction order can be non-integer values and can be negative. However, the most common that we are going to study is 0, 1, and 2. And I said there are the coefficients here, but it is important to know that the reaction orders do not necessarily correspond to this coefficient in the balance equation. So if we have a set of data, if I want to give you an example, for example, we have a set of data, for example, then the reaction is CH3 Cl chloride plus C and carbon Cl4 plus 3 HCl, and the following data for it is XP CH3Cl concentration, Cl2 concentration, and initial rate. So the experiment 1, 2, and 3. This is 0.0 0.05, 0.05, 0.014, 0.029, 0.115, 0.05, 0.2, 0.1, and 0.2. So I want you guys to stop, think about this question, stop the video and try to solve it. Write an expression for the rate law. What is the overall order of the reaction? And calculate the value of the rate constant with the unit K. So if you want to write an expression for the rate law, it is important for us to first look at where do we have the constant concentration. So here, like the first two experiments, we have the same concentration here. So to find the rate to write the rate law, we consider this, and then we're going to like calculate and try to write the rate for it, because it would be easier to find it, because the effect of changing the concentration of one reactant on rate while keeping the other reactant concentration is constant would makes it easier to find the rate, because it would be the Cl2 here, for example, is constant while the CH3L is changing, and now we just have to like consider the rate over the CH3Cl, and that's what it's affecting the rate. We do not need to calculate the other consider Cl2 over it. And how we do it's just a simple math here. Rate 2 over rate 1 equals 2. I'm sorry. We have m here, if you guys still remember it, because the rate is K over 3 Cl times 2 Cl2 N, and since we don't have any change in Cl2, we just don't need to consider this. And this one is for the concentration of second one is 0.1 molar, and this one is 0.05 molar. The final last answer would be, I want to find the order of this reaction. So rate 1 over rate 2, it's 0.029 over 0.014, and this one is almost 2. Almost. And this one again is almost 2, because it's twice of that, so 2 with the power of m. So m here is 1. So what does it show now? Since we have the m now, we can easily calculate for the Cl, because we know the effect of m and the order of CH3Cl, and we just need to use the other two, like this here and that one, to find the our n for Cl2, and just write the rate law. To calculate the order of Cl2, we just need to do the same thing. So again, 0.115 over 0.029 equals to K times 0.2 times 0.2 over K 0.1 times 0.5. So the overall answer for this would be to the power of n 8, and this one is, it's almost 4. So 4 equals to 8 to the power of n. So what is n now? N is 2/3. It's 2/3. And the order of the reaction for Cl2 is 2/3. What is the rate law for this equation now? It's K times CH3Cl and we found the m for it 1 times Cl2 with the order of 2/3. And that's how do we write the rate law. What is the overall order of the reaction? The overall order is 1 plus 2/3, which will be like 1.66. And to calculate the value of the rate constant, use the data. Like, we can use any of the data to solve it, and every time that you use it, you will get the same value of the k. So k is equal to, for example, I'm trying to, like, for the first one, the rate was 0.014 molar per second. The second one was, and it was 0.05, and with the power of 1 for the C3Cl, and for the other one again was 0.05, and with the power 2/3. And you just have to calculate it, and every time that you try it, so with every like other set of data, you will get the same answer for it. And now let's go for the units of the rate constant k and the change of concentration with time, 0 order, first order, and second order. So units of rate constants. So the rate of reaction will always be in the units of mole times liters. So, okay, let me just write it down. The rate of reaction will always be in units of mole. And the concentration of reactants will always be in moles per liter. Like, per liter. This one, moles per liter per second. The units of rate constant for a particular reaction will depend on the overall. It depends on the overall order of the rate law. And for example, the units for the rate constant in the reaction of, yeah, this one is a good example to show to you guys. For N2O5 produces 4NO2 plus O2. Well, I don't have the numbers now, but if you, the rate is N2O5, if you calculate the rate of N2O5, it's a first order. So this one is first order. And the rate for it would be, to find the rate constant for it, you just have to divide rate by the N2O5, and you will get the value of seconds. So the unit for the first order is this. And if I want to give you a summary for it, if the for the order of reaction, units of k, and example of the rate law. So for 0, 1, 2, 0, 1, 2, 2, 3. Units of k are mole liters per second, seconds, and per second, mole negative liters seconds, mole with the power of -2, liters with the power of 2, and seconds with the power of 1, -1. And this one rate would be k, just k. This is 0 order, so everything with the power of 0 is 1, so we do not consider the concentration. The rate would be k over a times the concentration of a. Rate for the second order, it can be whether a with the power of 2 or k a b. For the third order, and can be again rate for it would be k a with the power of 3, and so on, and others. So integrated rate law. So rate laws allow us to calculate the rate of reaction, but we can use the integrated rate laws to calculate the concentration of reaction at any time during the course of the reaction. And we must use calculus to derive expression for the integrated rate laws for the like reactions orders like zeros, first and second. And I guess you guys are not responsible to memorize them, and they will give you on the cheat sheet, and you can use it on cheat sheet or the reference sheet that you have on the exam. So if you want to start with a zeros order, the rate of zero order is just k, right? As we said here, the rate is just k. And if you want to rearrange it, the integrated of a at time interval t, concentration of a at time to 0, and we use the, as you guys know, minus is equal to the concentration of a at t, a concentration t 0, I'm sorry, it's negative k dt. So it just, if you put a t here, concentration of a at t here, and the concentration of a at 0 here, so it will be concentration of a at t minus concentration of a at 0 equals to the d would cancels out with the integrated, so it's just negative k t. And okay, now we go for the like, we can rearrange it, and we can put that one over here. So the concentration of AT is equal to negative KT plus concentration of A0. Notice that it's similar to the linear reaction. So Y is equal to the mx plus B. So notice that K is the slope of our graph, B is the intercept, and X is our variable here. And the K is negative, so the slope of a reaction of a zeros order is negative. Negative K, slope, delta Y, delta X. This is our concentration, and slope is negative K. Here is time, and this is our intercept, A0. For the first order reaction, that one's for the zeros order. For the first order, what a bad writing. Again, we say rate is negative d concentration of A over dt. It's Ka. Notice that this is the slope, so that's it. And if you rearrange it again, the integrated of, again, AT is 0, d a t 0 negative k dt would give us a natural logarithm of, sorry guys, natural logarithm of a t a 0 equals to negative k t. And notice that when we, in a natural logarithm, when we like divide, it's almost similar to always use this equation. Or so if we, like for example, say the natural logarithm of, for example, a minus natural logarithm of b is equal to the natural logarithm of a over b, and we can simplify it into that form. So, but this one is also equal to the natural logarithm of a minus natural logarithm of b equals to the negative kt. I'm sorry, we don't have b here. Natural logarithm of a t minus natural logarithm of a 0. So again, we can put that one over there. Natural logarithm of at equals to the negative kt plus ln of a 0. Again, it's y equal to the mx b. Again, same format, slope, time. Again, here there is a ln of a, and that slope would give us a negative k, and that's the intercept of our b, so it's ln of a 0. For the second order, there's something special about the second order. For the rate of second order is k delta a with the power of 2. And if we want to derive that formula, I can just drive it. Like, I don't want to waste your time. So it would be just 1 over concentration of A at T equals to the KT plus 1 over concentration of A 0. And again, it's just like that, mx plus b. However, notice that we have a positive concentration here, positive slope here. So our graph would look something like this. This is our intercept, which is a 1 over a 0, and this is our slope. The slope would be positive k. Here, notice that these are negative k. Here is negative k, but here we have a positive k. And yep, that's it. If I want to I can give an overall, but you guys can like review it. Never mind, I would write that. Okay, this is the order 0, 1, 2. The rate law is Ka0, which is 1, just K. This one is Ka, and this one is Ka2. The units of K would be molar, second, negative, second, and okay, and integrated would be negative KT plus 0. For the reverse order, this one is ln of AT negative KT plus ln of A0, and then we can just show it like this. I don't want to write it. Where is it? It's the reverse order. No, it's here. Yeah, we can write it like this. This is an important one. And for the second order, it's just 1 over concentration of A at time interval t equals to the KT with a positive K over plus 1 over A t, and their graph would look like this. Negative slope. Now let me just show it like on date reach 0. Okay, 0, and this one is go up, positive K. So now if there's let's try to solve an example. I will give you guys an example and you just try to solve. So the question asks for the decomposition. I hope you guys stop the video and try to solve it, then again continue the video, check your answer for it. So it says for the decomposition of reaction B products, a plot of ln B versus time yielded a straight line with a slope of negative 3.35. So when it says it yielded, first, again, how can you determine what order reaction is it? What reaction order is it? It says a plot of ln B. So which one had ln plot? The first order reaction. And another thing is you can say, okay, the slope was negative 0.35, so it cannot be the second order, so it's just better the zeros in first, and it says the ln, so it's just the first order. And for part A, it says if concentration of B at time 0 is 0.16, find B at t equal to 4 minutes. So we just put it in the formula. So the formula was ln of concentration B at time t over B at time 0 is negative kt. Again, why did we use an integrated rate law? Because we have time here. And I hope you guys know how to calculate, to find it's just a calculus. So ln is log e. So if we put e here, like we say, okay, e with the power of ln bt over b0, okay, equals to the e with the power of negative kt. And so again, e itself is like log e, and e with the power of log e would be just 1, and then it's just some simple calculus. And this one would cancel each other out, like we have a number here which is bt. So the overall would be, this is just a general rule, like e with the power of log e something, b for example, this one is equal to 1, and this one goes out, so it's just b time multiplies by 1, so it's the same thing. Let me just write, so this one will be, these would cancel each other out, and it would be concentration of B. Sorry guys, I haven't solved them, so I'm trying to be sure. That's why I'm pausing. And so it's just, this one goes here, B T over B0 and equals to the E negative KT. So we want to find the concentration of B at the time interval of 4. So we want to put it over there. So we just try to multiply it by B, concentration of B at time interval of 0, cancel each other's out, and just it goes that way. So the concentration of B at time interval t is equal to the B time interval of 0 multiplied by E with the power of negative kt. And our initial concentration was, let me write it like this. Our initial concentration was 0.6 molar times the E with the power of negative. The rate of reaction was negative 0.35, and times to the 4 minutes. In 4 minutes, I didn't change the units of time because the rate was in minutes and the reaction wants it in minutes, so we don't need to change anything. And if we try to calculate it, E 0.35 times 4, the answer would be the concentration of B at T 0.0395 molar. And you guys can try to make sense of your answer. Does it right or not? We said, so it's just our product was consumed, okay? So what it means is that over time we should have less concentrated of B here. So the initial concentration was 0.16 molar, and now we're at 0.0395 molar. So it does make sense. If you get a number higher than that, so there must be something wrong with your answer. And that one is answer for part A. For part B, it says find the time required for the concentration of B to drop from initial B to 0.1. Again, same formula. Ln of concentration BT. I'm sorry guys, I have to write it outside the bracket, but it just a habit of mine. B0 equals to negative KT, and again ln of 0.1, 0.16 equals to the negative 3, 0. Because that's our rate, 0.35 times t, and if you calculate this answer, it would be negative 0.47 equals to the 0.35 minutes times t. What is this t here? Min t, and our t, we just have, to calculate the t, we just have to like say negative 0.47 or negative 0.35. The answer would be 1.34 minutes. And again, make sense of it. So after 4 minutes, what we were left was 0.0395 molar. And after 4 minutes, and now at 1.34 minutes, we just had that. So it's similar. So it should, so if you get higher than 4 minutes, so your answer is somewhere wrong. And like, if you look at it, it's like this 1.30, okay, this one, try to compare it with a 0.5 molar. It's almost 3 times less than 3 times of this one. And also compare the time, 4 to 1.34. It's also less than 3, because if you multiply it by 3, we get more than 4 minutes. So I just want you to like let you notice that the relation between them. And for part C, it says find the time required for the half of B to decompose. Again, same formula. And so, but the difference is BT over B0 should be half. So ln of half should be negative 0.35 t. And if you calculate it, it would be 1.98 minutes. And again, notice the half of like 0.16 is 0.08, and it's less than 0.139, so you can say that your answer is right. And yep, that's how we calculate it. And now let's go for half time. Let's say if there is, okay, should I? Yeah, I would try to explain it in another video, half time and activation energy. I hope you guys have won't have any problem on it. If you do, please comment it on the video, like and subscribe it, and I would be happy to see your reaction of the video.